All right, so finish up this chapter. We want to go through the stepwise calculation of pH values as a function of adding a titrant into a given solution. In this case, we're going to be titrating a strong acid with a strong base. And in essence, there's some things you need to keep in mind. If this is your burette, we're going to have the strong base in the burette, and of course in the beaker we're going to have, of course, the strong acid. Well, as we go through the titration, the addition of the base will be a limiting reagent or reactant, because you recall, as you add this one, it's completely consumed in the solution and converted to a salt, reducing the amount of acid until we reach the equivalence point. And what you'll see, as we've drawn several times, volume of base added into the acid starts with a low pH, goes along and follows this trend. Of course, we'll go through pH 7 at the VEQ and so forth. So what we're going to do here is we're going to take 25 milliliters of 0.10 molar HCl, and then add plus 0.10 molar sodium hydroxide in increments, volume increments. So we'll start with, say, 10 milliliters, and then go to ml, and then go to 24.5 ml, and 25 ml, which is will reach the equivalence point. Anything above 25 is simply adding an excess of base, and you shove the pH up in here. But until you get to the equivalence point, everything's a limiting reactant problem up to that point. So essentially, our first problem is simply written like this, or a 10 milliliters of 0.10 molar sodium hydroxide added into 25 milliliters of 0.10 molar HCl. The question is, what's the pH? Okay, well, we know what the pH is before we start. Okay, we can say at before titration, pH equals 1. The minus log of 0.1 is 1. So and so we opened up the stopcock in our titration and let in 10 mils of our 0.1 molar solution, and then read the pH value. Well, in this case, I'm showing you how to do the calculation for it. Now, these are the reactants of the HCl, write it out, NaOH plus HCl goes to NaCl plus H2O. So all I'm showing you is the reactants. I don't care what's on the product side right now. Now, when we get to weak acid, strong base, yeah, I'll have to put that in because it's going to give you a common ion over there. And so on that side. So here, what I do is I write down the reactants that are coming together and the volumes, 10 mils into 25 mils, and then these I'll convert to moles and then molarities. And then from that, one's in excess and one's consumed. Now, the base is the limiting reagent, so it'll be going out. So what we're really doing is finding out what's remaining in terms of the acid, and then that'll give me the hydronium and the pH. So here we want to go to 0.010, well, I'm just 0.1 liters times 0.1 mole of sodium hydroxide plus 0.025 times 0.1 mole hydrochloric acid. Okay, and it's a 1-to-1 reaction ratio, and so it's a 0.001 mole sodium hydroxide plus 0.0025 mole of the HCl. So we take this into account. So if I'm adding 0.001 mole of sodium hydroxide in a 1-to-1 reaction, how much of the HCl am I going to use? Only 0.001. So the excess HCl and all the NaOH is gone when you drop it in the beaker because it's a limiting reagent. So this is a 0.0025 minus 0.0010 mole of HCl in remaining. In the beaker. But it's 25 plus 10 or 35 mils of it now. So we have to get molarity using that. So this goes to 0.0015 mole of HCl in 35 milliliters, 25 and 10 milliliters of solution. So to get the molarity now, it's moles over liters, so that'd be 0.0015 mole HCl divided by 0.035 liters. This HCl, and that is 0.043 molar in HCl remaining. Like that. And since this is a strong acid, this gives me my hydronium ion concentration to equal the remaining concentration of HCl, which is equal to 0.043 molar, and therefore the pH, after adding the first 10 mils, of base, is minus log of this. So we move to 1.37. So we started at pH of 1, and then we added in the quantity of base. And so since the base is neutralizing acid and converting it to salt, we have less acid in there. That is, we're moving more to the base range. So therein is the reason for the increase in pH. Now, what you're seeing now is in the titration, we started at, say, 1. Now, after 10 mils addition, we're barely up a little bit, like that. And so when I go to, let's see, 1, 2, 3, 4, 1, 2, 3, 4, to the 20 milliliter addition, oh, see, I did 15 next, didn't I? So when I go to the 15 mil, I can change that to 20. And we move on quicker. I'll move that to 20. Let's do a 20 milliliters. Then you will see some more increase, but it's not going to be that much. Not until what? And you remember me barking about the theoretical calculation, and so you'll find out like 25 and 25. You know it's going to neutralize at 25 against 25. If you have a 0.1 base and a 0.1 acid, and you have 25 mils of the acid, you're going to need 25 mils of this to get your equivalence point. So we get up in here to the 20, and so 20, I don't know, I'm just going to exaggerate this, right here, say it's 24 point, what did I say, 24.5, yeah, mils, right there. You'll be surprised, it's not going to, it will not get to the 7. It won't show very close to 7 yet. But this is what you should expect as you go through each one of the gradients. This is going to shoot straight up, kind of like this, toward the 7 up here, but it's going to be back down here in the 4 range or something like that. So watch for that as we go through the next calculation. We'll do a 20 mil calculation. Now, in each one of these, you have to start over. You assume 0, and then you're going to put so many mils in on the beaker volume and concentration. Okay. I'll just make that 2 is 20 mils of 0.10 molar NaOH plus what have we got? 25 milliliters of 0.10 molar HCl. And again, we want to convert to moles, so that means molarity times volume in liters. So molarity times volume gives you moles, plus here on the HCl is 0.025 liter times 0.10 molar, and that gives you moles of HCl. And that'd be 0.0020 mole NaOH plus 0.0025 mole of HCl. So again, it's a 1-to-1 reaction ratio with the sodium hydroxide being the limiting reagent, so it's really not going to be there until we get past the equivalence point. So we subtract those two, 0.0025 minus 0.0020 mole HCl remaining. It is a 0.0005 mole of HCl remaining. Okay, see the kind of the trend. Of course, the calculation of the pH is minus log of the hydronium ion concentration moles per liter. Now, this is giving you a 0.005 mole of hydronium ions as well as the HCl, but the molar concentration of HCl now, which will give you the hydronium ion, is now 0.0005 mole over, now we've mixed 20 and 25, we're now up to 45 mils in our solution. And in liters, that's 0.045 liters, and that translates to be 0.0005 divided by 0.045 equals 0.011 molar H plus. Okay, and the pH minus log of the 0.011. So now we're up to 1.95 on our titration curve. So we started at 1, then we went up to wherever that went before. I don't even remember, 1.337, yeah. And so right here is a 1.37. And so that's after 10, and 1, 2, 3, 4, 1, 2, 3, 4. That's about right. 20 mils. And so that goes up to 2. So that's 1, and then up to 2. Just under 2, 1.95. So you can see how it's kind of creeping up toward the higher values. And so now we want to go to 24.5 and do the same thing, see how close it gets to the pH of 7. So here we're going 24.5 milliliters of the 0.10 molar sodium hydroxide plus 25 milliliters, the same concentration, HCl. So what do we do first? Convert to moles. 0.0245 times 0.10 mole plus 0.025, 0.10 mole HCl, 0.00245 mole sodium hydroxide. Once you get in the rhythm of this thing, you just scoot right along on it. So that'd be 0.00250 minus 0.00245 mole HCl remains. And so I'm going to trust my brain here. Okay, that's 5 times 10 to the minus 5 mole of HCl remaining. Which gives us a 5 times 10 to the minus 5 mole and 24.5 plus 25, so that's 29.5 mils, or 0.295 liter. And I got a 0. Or I put it in exponential, 1.69 times 10 to the minus 3 molar in HCl, which is equal to our concentration also of the hydronium ion concentration right here. And so the pH, after adding 24.5 mils minus log of that 1.69 times 10 to the minus 3 button. Notice 2.78. So we're, even after adding that much of the base, we're not hitting on the close to the 7. Okay, so you can see how we're getting closer and closer to the equivalence point. Through this one and titrate with the same 0.1 molar NaOH, we have to take into account the generation of the salt, and that salt is generating a common ion. So when you make your calculation and you set up your ice table, you have to put in that conjugate base in here. So this is a, did I start it? Yeah. This is a weak acid plus strong base titration. And so what we're going to do is we're going to use base. We're going to 0.10 molar sodium hydroxide plus 25 milliliters of 0.10 molar acetic acid. And we're going to check it at 10, 20, 24, 5, 25, 24, 9, 24, 9, 9, or whatever we want to calculate. But the one thing at the end, at the equivalence point here, you're going to wind up with nothing but salt, just like you did in the strong. But that salt, the salt that's generated, let me show you, NaOH plus HOAC, when you reach the equivalence point, you have a sodium acetate. And you have to do all you have is this, and you have to do an hydrolysis calculation. Remember how we tested it with the ions with water? And then you plug in an ice table with that one. And that's what generates the hydronium ion you need. This will give an excess of base. Remember, sodium's not going to hydrolyze. I'm just going to show you this plus HOH. This being the negative portion and that being the positive portion. Of course, it's going to pull the H over. And this is your hydrolysis reaction. And then we build an ice table off of this one and calculate the excess hydroxide and then POH, pH, and at the equivalence point. But this is at equivalence point. But until we get to the equivalence point, all we're doing is an HOAC hasn't been completely neutralized, and but we have a common ion in the OAC as we go through each of the titrations. Okay, so watch for that as I go through, and I'll repeat them. Okay, so our first calculation is 10 milliliters of 0.10 molar sodium hydroxide plus 25 milliliters of 0.10 molar acetic acid. And so this is going to give you a 0.0010 mole. I hope I'm just skipping over. Molarity times volume again. Sodium hydroxide plus 0.0025 mole of the acetic acid. Now we have to convert to molarities. So we have 10 and 25, 35. So this is 0.0010 over 0.035 liter of sodium hydroxide plus 0.0025 mole per liter, 0.035 milliliter, like we did in the other calculations. And so whatever this gives us. But we have to keep in mind this is gone, but in the sodium hydroxide will account for the yield of the salt. So whatever we calculate here in molarity of the sodium hydroxide used up is also equal to the salt generated in the reaction. I'll show you. Get these down, 0.001 divided by 0.035, and that gives us a 0.0286 molar, I get picky, sodium hydroxide used will, and which is equal to 0.0286 molar in OAC minus formed. See back up here, see when I use up so much of the sodium hydroxide, I'm going to get the same amount 1-to-1 in the sodium acetate right there. So while I calculate that amount that's used from here, I also just make a note over here that that's how much the salt I'm generating. And so now I can take, let me see what that one is, 0.0025 divided by 0.035, and that's 0.071 molar in that one. If you read my scribble, 0.71. So in the HOAC, well, all of the NaOH is gone. 0.071 molar HOAC remaining. So this is where students, in my experience, have struggled because they don't see that salt being formed while you're using up your sodium hydroxide. And what this gives us is, like in the previous calculations when we were using strong, this was the HCl. Well, it was also equal to H because it was a strong acid. But here we have a 0.071 molar HOAC. And so you have to take into account plus the conjugate base over here and put it in the ice table. So now we have HOAC in equilibrium, because that's what's left. So you've reduced your HOAC, but it's still ionizing to deliver hydrogen and the conjugate base into the system, like that. And so the remaining HOAC is 0.071 molar. We've already converted. And this is 0, and the conjugate base is 0.0286 molar. Okay, so look at that critically right now, and so be sure you understand what I did. It's still an acid plus base up here, acid plus base, and since the base is the limiting reagent, it's being consumed. But note, it's also producing the conjugate base that's going to undergo hydrolysis or be the common ion. So that's your common ion concentration, and then you go through your changes to get to equilibrium and apply this to your equilibrium expression. So minus X plus X plus X, and you can drop that X now, and 0.071 molar X and 0.0286 molar. Because when you get to that point, that common ion is going to reduce the extent of reaction. So if you can drop it in pure water, you can certainly drop it in the presence of a common ion, that X, that value, that is. And so from here, Ka equals H times OAC, forgive my symbology lack. And so that's equal to 1.8 times 10 to the minus 5. And we're looking for the hydronium ion. The conjugate base is 0.0286 molar, and the weak acid is 0.071 molar now. So this you want to solve for your hydronium and then take the minus log. Oh, wait a minute, that's OH, isn't it? No, that's right. Right. Okay. Yeah. I'm thinking hydrolysis. 1.8 times 10 to the minus 5, 0.071, 0.0286 molar. .071. I get 4.47 times 10 to the minus 5 molar in hydroniums. I'm going to do that again just to be sure I didn't miss a button. Yes. And then I hit the log button on that, and we have 4.34. So pH now, minus log of 4.47 times 10 to the minus 5 is equal to 4.35. Okay, that's after 10 mils of 0.10 molar NaOH is what the system is. Let me show you something real quick here. So what we're looking at now in the titration, I didn't calculate before addition of base. Up there. So hydronium ion is equal to square root of 1.8 times 10 to the minus 5 Ka times the 0.1, 10 to the minus 1, and I think it's 4.74, I believe. Let me check that. It's 2.87, excuse me. 2.87. This is before we started adding anything into it. Now I have to use the square root for it. I forgot to do that for you. So we're starting down here at 2.87 at 0 volume of base, and then after 10 milliliters, 1, 2, 3, 4, 5, 10 mils, we've jumped up to 4.3. That's almost 3, 4, say right here. See, let's say that's 2, 3. Let's see, yes. Make that 2. That's 3, 4. Would it be right in there? 4.3. So the pH jumped up to 4.35. So we've titrated to there. Now if we go another 1, 2, 3, 4, 5, go to 20 mils and repeat and see where that goes. Okay, is 20 mils sodium hydroxide. And so 0.0020 mole, 0.0025 mole, and so this will give me a 0.0025 minus 0.0020 and 0. And it's 0.0005 mole HOAC, which gives us a 0.0005 mole over 20 and 25, 45, 0.045 liter. And again, it's 0.011 molar in HOAC. But also, we used 0.002 mole of the sodium hydroxide. We have 0.0020 OAC generated in the same 0.045 liter. So 0.044 molar in the acetate. So now with these two, we apply it to the Ka expression and the ice table. So we'll have HOAC H plus OAC, CI, change at C, and C at equilibrium. And so we're 0.011 molar, 0, and 0.044 molar. If I did that right, okay. And then minus X plus X plus X, and these will give you 0.011 molar X and 0.044 molar. So Ka So hydrogen after 20 mils is 1.8 times 10 to the minus 5, 0.011, 0.044 molar. I'm just repeating everything. Times 1.8 to 10 to the minus 5 equals 0.044. Second scientific. 1.82 times 10 to the minus 5 molar in hydrogen. And so the pH now is minus log of that number. Which gives you 4.75 or 74. So now we've gone through the 4.35 and then 4.74, and so it continues. The procedure is the same, 2.7 something or another, and then went on up to 3.74, I guess it was, I don't remember. And then we're going up to 4.74, and this is of course the volume of base and pH, and it'll keep going like that and start scooting on up to the equivalence point like that. Okay, so what is the pH at equal volumes of equal molar concentration? So if we have 25 milliliters of 0.10 molar sodium hydroxide reacting with 25 milliliters of 0.10 molar acetic acid. The outcome of this is 50 milliliters of 0. I better calculate it. I think it's 0. I better do it. It's the amount of sodium hydroxide used. So this will give me a 0.02025 mole over 50, 0.050 liters of the sodium acetate. That's what I want to be sure I've got the right number on. And so that is a 0.005. A 0.05 molar OAC minus. Right there. Double check. Yeah, 0.05 molar. So this is at equivalence point. And so what this says is you have to apply a hydrolysis calculation. And what that means is react it with water, OAC minus, plus H2O. Now what will that go to? Well, of course, that's going to be that reaction that pulls off the OH. This is minus, and of course that's plus. And so negative is going to pull off the plus and leave you an excess of hydroxides. And so that's going to give you an HOAC plus an excess of hydroxide. So that's going to be your hydrolysis reaction at the equivalence point. And so from the calculation of concentration at the equivalence point of that is 0.05 molar. Ignore that, and we start 0 and 0, and set up the ice table. Minus x, ignore, plus x, and so at equivalence 0.05 minus x, and x, and this is, you can drop the x here. So there's your your equilibrium concentrations for the hydrolysis reaction. Everybody good up to this point? Take pictures. I'm out of paper again. Maybe I can get it all in here. Okay, at this point, it's a KB prime. You recall all conjugate bases are KB primes. If you were working a cation, it'd be a Ka prime. And the calculation of the Kb prime is Kw over whatever acid is generated, Ka. Kw over, Ka value for that acid. And now that is equal to the products over reactants, ignoring water. We'll have HOAC concentration, which will be X, and the OH concentration, which is also X, which is what we need, and then the salt concentration. And so this was 1X, and that one's the other one, and then your salt concentration, 0.05, goes right there. That's X squared over 0.05, and that's equal to 10 to the minus 14, and the Ka for HOAC is 1.8 times 10 to the minus 5. Solving for X, which is your hydroxide, which is the square root of 10 to the minus 14 times 0.05, divided by 1.85 times 10 to the minus 5. Now this comes out in moles per liter. Let's see if I can squeeze that in there. So we're now at 5.27 times 10 to the minus 6 molar in OH ions. Okay, now I just go straight into the POH and then the pH at the equivalence point. 5.27 times 10 to the, what in the world? Is this up? Right up here. Minus 6. There we go. And hit the log button, and that's a 5.28. Now don't get confused here, because that's the POH. And so you got one more calculation here. And okay, I hope you can see this, because I am out of paper. Wait a minute. Just take it loose. Move it up here so everybody can see what's going on. This is the last line anyway. pH is 14 minus POH. 14 minus 5.28. And that gives me an 8.72 at equivalence point. And that, my friends, is how you do titration calculation.